Right, good morning, good afternoon again, people of the world. We continue to the second part of this R1.4, which is Gibbs free chains or delta G. I remembered I said to you that this is one of the most powerful chemistry law, and it's not only according to me. As you can see here, this is one of the most important relationship in chemistry. So again, your objective today is to understand these equations. Very simple, although uh, there's a lot of weird terms in here, but delta S we've covered before, the entropy change. Entropy definitions is it's terms to say about dispersal or disorderness of the molecules and energy. Delta H enthalpy is the total energy in a molecules, and the delta G is Gibbs energy change or free Gibbs energy or kind of stuff. So this is really what you call it, yeah, abstract, but once you understand the function of these equations, you're gonna understand why this is, hopefully, yeah, why this is so important in chemistry. So to start with, I'm going to uh, ask you to think about our natural instinct, intuition toward the natural phenomena in this world. So like natural instinct, natural intuition, like for example, if you have water like this, and then you kind of like put it here, and then you tilt it the bottle so that the position of this water is a little bit higher than your mouth, then that's like there is a natural intuition for you expecting the water will flow toward your mouth, because we have this natural intuition that if you put water in a higher positions because of the gravity and stuff, it's going to flowing down. And this natural intuition about the flow of water is easy for us to understand, because of course water will flow down if you put it above you and stuff. And then for example, another natural intuition, like um, if you jump into the pool and then there is water in it, you're gonna drown in it, right? That's spontaneity that come to your mind. That's how natural behave. That's a law of nature that we can understand those stuff intuitively, right? Like if you have fire, and then you put your hand on it, you're gonna feel very hot and burn. You know on your mind that's going to happen naturally, spontaneously. So a lot of things in this nature you can just intuit, because you've been exposed to those observation for so long, and then you're going to automatically have this intuition what's going to happen if you have that and that. Now that's what we call it spontaneity in the nature. It will happen because it's just how nature works. They're just going to just happen like that. So but then in chemical reactions, it will be useful if we know which chemical reactions that will naturally occurs, and then will spontaneously occurs. It will be useful for us to know whether the chemical reaction will be able to proceed or not. Okay, so the way you look at how water will flow from the upstream to downstreams, that kind of mentality, that kind of instinct, you can have that because you know that you've been observing this all of the time. So there is no questions that will happen, that will occur, those process. Now we're going to use these equations to be able to determine whether a reaction will spontaneously happening or occurs just like the water flowing down like that. So this is powerful because we will understand that this reaction is possible to happen or not, naturally or spontaneously. right? So again, that's your goal after this, to understand whether the reaction will be able to happen spontaneously or not. Now, to understand this, again, I'm going to go with the video from this guy, very, very good, explaining the spontaneous reaction. And then this guy explained to us that the delta G, we don't, um, we can say that delta G is the available energy in the system that can be used to do the reaction itself, or the works. So if there is energy obtained, if there is energy available, then they are able to do the reaction, something like that. So this guy over here giving us the we call it the definition of this delta, not the definition, the relationship in the delta G equations very, very carefully. So in this first part, we want to talk about the enthalpy, like the total energy in the system, and we are going to see the three different spontaneous phenomena, which is this very big ping ball slide over here, slide down here. So you're going to think automatically, if that happen, intuitively you can say that the ball will go down, right? Must be like that. That's naturally happen. The second one is diffusion reaction. So if you have a gas and you have this barrier, if you, and this is empty space, for example, this is gas, and then if you open this barrier, you're going to think automatically the gas must be do the diffusion, like the gas will be going over all of this room, right? That's you're thinking already, it will be like that. That's how nature works. And then if you have this cherry bomb, you're gonna think directly, if you have this fire over here, the fire will go in here and then it's going to explode. There must be explosion. So these are three spontaneous phenomena, and we are going to break down these three spontaneous phenomena to then understand these equations. Okay, so the first phenomena will be about delta enthalpy. The second phenomena, the diffusion of gas, will be about entropy. And then the cherry bomb will be about temperature. How these three things affect spontaneity of a reaction. These three different things will be able to tell us whether the reaction is spontaneous or not. It will happen or not, naturally. So let's see here. So not this one. So this guy over here. Let's see this. Okay. So again, the ball will just slide down like that, and then what makes that happen, the total energy, if the ball is in this position, the potential gravity will be higher than will be big, yeah. The total energy in there is potential gravity. And then if you let it slide down like that, the potential gravity here in this position will be lower than potential energy in here. Potential energy, the total energy is delta H in there. So it will change from the big H to the small h, meaning that the enthalpy from the beginning to end is decreased. The enthalpy change is product minus reactant, will be negative. So in spontaneous reaction, the enthalpy change is negative, is decreasing, okay? Remember that enthalpy change is decreasing. Just remember this ball sliding down. If they are in the lower position like that, the potential gravity energy will be lower than if you put the ball in the upper position like that. Now the second one is the diffusion. The diffusion in here will give you the idea about entropy, disorderness or dispersalness of a situation. So if you have the barrier in here, so this is the before the reactions, and then when you open this barrier, the gas will then go that way. It means the disorderness now increasing, right? The spontaneous reactions in here saying that the relation with the entropy, it's saying that if you increase the disorderness, if you increase the dispersed level of a molecules, that will be the spontaneous reactions. So you will have to make the entropy change become positive, become more disorder. That's the character of spontaneous reaction. So repeat again, with the enthalpy change, you want the enthalpy at the end lower than enthalpy in the beginning. That's why the delta enthalpy has to be negative. But in the disorderness, you want the other way around. The entropy after the reaction must be bigger than entropy before reaction. Okay, you need to pause this if you want and then repeat again. The third one is the cherry bomb. So the cherry bomb essentially is if you have if you increase the temperature, like this cherry bomb will explode when you have fire in it. It means, and that's spontaneous reaction. So what you want, if you want to have these spontaneous explosions, you need to increase the temperature. So this is the temperature before and after, before explosion and after, compared to after explosion will be lower, or the temperature after explosion will be higher. So this is kind of the same with entropy. You want to have higher value on temperature when you want to have spontaneous reaction, right? Now take a look at this reaction, this equation again. So remember, the enthalpy want to be negative because you want the ball having lower enthalpy. The temperature you want to be higher if you want to have spontaneity, and the entropy change has to be also higher. So here's the thing. If you imagine this is an equation like that, just directly go here. If you decrease the enthalpy change, the delta G will also decrease, right? Because imagine this is 5 and then this is 3. 5 minus 3 compared to, let's say, 4 minus 3, obviously the result in here will be lower. It's a simple algebra. If the algebra is like this, the equation like this, if you lower this delta H, the delta G will also be lower. If you increase this value, the delta S, the delta G also will be lower, and the temperature also the same. If you increase the temperature, the delta G also will be negative. And why we need to lower this? Because according to the previous phenomena, you know that the enthalpy has to be lower, will be minus, yeah, because enthalpy change, total energy must be decreasing. The temperature, cherry bomb, has to be higher to have spontaneity, and then the delta S or the entropy has to be higher, more disorder. Now if you combine this algebra, you decrease this, you increase this part, delta G will be low or negative. That's why this is the key. If you have delta G less, the value of delta G is less than 0, it means that the reaction is spontaneous. If the delta G is more than 0, it means it's not spontaneous reaction. It's hard to understand, but just try yourself first to understand these three things together. My suggestion to you to watch this video of this bossman and really understand about these three spontaneous phenomena. Your goal is to understand delta G negative, because that's the indication for a chemist to then predict the reaction will be spontaneous. Okay, that's it. Try to understand this as hard as you can. Repeat the video. Thanks, guys. Good luck.